Yeah, next speaker is Francesco Montorsi. He will be talking about ultrafast pump probe spectroscopy simulation in OpenMolcas. Floor is yours. Enjoy.
Okay, thanks for the kind introduction. Today I'm going to talk about this topic basically, and I'm going to show some kind of application of OpenMolcas in the context of ultrafast spectroscopy simulation, and I will do this kind of study from the UV visible regime to the X-ray regime. But first, I want to start with some of background on ultrafast spectroscopy. So basically, what is this kind of technique, why it is interesting, and what kind of processes are going on in this kind of experiment. Then I will move on the molecular target that I'm studying right now, which is the nicotinamide adenine nucleotide dimer, NADH. And then I will show basically how we can model ultrafast spectroscopy signals starting from this kind of system. And finally, I will analyze the result and try to discuss what kind of physical information we can grasp out of it. So, in this kind of experiment in ultrafast spectroscopy, we use a first intense pulse, which is called the pump pulse, to prepare the system in a given excited state, and then with a second pulse, which have a given time delay from the first one, we probe the state of the system. And in this kind of experiment, we can have several processes that can take place. For example, the probe pulse can excite the previously excited state, which is prepared by the pump, and in this case we are talking about excited state absorption, and we visualize it as a negative signal in the spectrum. Or the probe pulse can de-excite the excited state prepared by the pump, and in this case we are talking about stimulus emission. Or simply the probe pulse can interact with the fraction of molecule which is still in the ground state. In this case we are talking about ground state bleaching, and we also visualize it as a positive signal in the total stack. What I show until now is commonly called the one color scheme. So where the pump and the probe pulse are in the same energy window, but what we can do is actually select a probe pulse in a different energy window. And in this case, we are talking about a two-color experiment. In this case, we can no more see the stimulated emission, and we have a different mechanism for the ground state bleaching, but still we have this excited state absorption and ground state bleaching signals. Then let's move to the molecular target, which is an ADH. That this kind of chromophore is a biologically relevant molecule which can be found in nature in two different states, a folded and an unfolded states, according to the environment in which it is abandoned. For example, in water, we can see the folded conformation, while typically when the system is bound to a protein, it assumes an unfolded conformation. And what is interesting in the context of spectroscopy is that if we excite, if we prepare the system on the late state of adenine, then we can see an energy transfer, an ultrafast energy transfer taking place between adenine and nicotinamide. While if we excite the LA system, the LA state of adenine, we can only visualize the internal conversion to the ground state. And this is actually interesting because we have a spectroscopic fingerprint of the folding in this way, because the energy transfer can take place only in the folded conformation. What we know about this kind of process until now is that it is typically modeled as a Forster type energy transfer, and in this kind of process, the excited state of the donor, which is prepared by the pump pulse, is relaxing through its minimum, and then once it is here, resonantly transfers energy to the acceptor, which is in this case a nicotinamide. But the recent experiments show that this process takes place in sub 100 femtoseconds, which is actually the regime of the vibration relaxation, and so it can be simple at Fonster type energy transfer. So recent quantum dynamics simulation based on MCTDA on linear vibronic coupling model parameterized at extended multi-state CASPT2, which are run in collaboration with the group of Fabrizio Santoro in Pisa, show that this kind of process can be addressed as a non-adiabatic coherent process accelerated by a dark charge transfer state. And what we want to do today is to find what kind of transient experiment is best suited to resolve this kind of process. But let's move on the modeling session. Since this kind of system is very flexible, we have to sample a lot of conformation that can be populated in water, and we do this by the means of molecular dynamics. On the top of this kind of snapshot that we produce by molecular dynamics, we run QMMM optimization in water, and we use this snapshot as a reference geometry for parameterizing the linear harmonic coupling and then for running the MCTDH quantum dynamics. But once we have this kind of description, we have to couple this quantum chemistry to spectroscopy in order to simulate the signals. And what we do is simply to select a reference geometry for the unfolded conformation and a reference geometry for the folded conformation, weight them by their relative weight, and assume that for the unfolded conformation, only the internal conversion can take place. And for the folded conformation, we use the mechanism provided by the quantum dynamics. Then we have to choose what kind of experiment we want to simulate. In particular, we want to use the pump pulse in the UV visible regime in order to trigger this kind of process. And for this purpose, we have to simulate an excited state manifold. But then we want to simulate UV visible quantum spectroscopy, and so again with the probe in the UV visible regime, but triggering higher line states, and so we have to compute a different excited state manifold. We want also to test the response of the system in the XUV regime, where the system can be ionized, and so we are looking to transient photoelectron spectroscopy, and we have to compute valence cationic state. Then we want to move to X-rays, and in this case we want to look at the transient near-edge X-ray absorption spectroscopy, which is the transient fashion of the same technique that Francesco showed this morning, and we have basically to compute core excited states. And finally, also in the X-rays, but at higher energy, we want to compute core cationic states in order to simulate transient photoelectron spectroscopy. And we do this at QMMM level of theory within the framework of Cobram, which is a software developed in Bologna, which is interfaced with OpenMolcas, and we use it in order to obtain the description of this excited state manifold at CASPT2 level of theory. Then we process all these quantum chemical ingredients through the spectral interface, and finally we use a spectrum to simulate the signals. So if we look now at what we get out from this simulation protocol, and we start from the UV visible quantum signal, we see that we can clearly identify a signature which is dying in time and which is an excited state absorption, and at the same time, which is rising in time, we see a stimulated emission. But in order to grasp as many information as possible, we can study individually the contribution to the total spectra. This is the one coming from the unfolded conformer. We see that it is basically the one that gives rise to this ESA, which is dying in time. And we can compare to the one produced by the LA state for the folded conformer, which is basically identical but with a different timing, because for this conformer, the charge transfer process and then the energy transfer is happening. Finally, we can watch to the signature of the charge transfer state, which is placed in a crowded region of the spectrum, and so it is undetectable actually, and also because it is an order of magnitude lower in intensity, so we can't clearly address the city state within this energy window. And if we look at nicotinamide, we have this kind of long-living signal, long-living ESA, and this counterpart, which is the long-living stimulated emission, which are the fingerprint of the charge transfer process. But due to the high spectral congestion of this window, the correct timing of the energy transfer is not directly assessed just looking at the spectrum, because the signal of the unfolded molecule covers partially the signal of the folded one. And so we can't clearly visualize the energy transfer process, and we for sure can't visualize the charge transfer process. If we move to transient photoelectron spectroscopy, now we see that things are changed. We have still a signal which is dying on time at higher energy, then we have a long-living signal which is rising on time, and we have also another short-living signal at lower energy. Again, if we look at each individual contribution, we have the one from the unfolded, which is at higher energy. Then we have the signal from the folded conformer, and we see that unless this excited state absorption comes from the same valence excited state, actually, the fact that we are probing the folded conformation change the energy of the LA, change the binding energy of the LA state, as you can see. And also in this experiment, we have a signature of the charge transfer, which is partially covered by the signature of the population of LA. And so again, we can't clearly visualize the charge transfer within this window. And finally, we have the signal of nicotinamide, which is clearly visible in the spectrum. So in this window, we can for sure visualize the energy transfer. We have also the correct timing of it, but we still are not able to visualize the charge transfer. If we want to, let's say, rationalize why the signal from LA coming from the folded conformer and the one coming from the unfolded conformer are so shifted in energy, we can watch at what happens when we ionize the molecule during the experiment. In this kind of process, we shine the sample with an high energy pulse, we create a cation, and then the surrounding environment responds in a polarizative way to this new positive charge. But if the molecule is in the folded conformer, the polarizative response of the higher molecules can stabilize even more the so created cationic state. And in this way, we have a rationale to explain why the signal coming from the folded conformer are redshifted compared to the one coming from the unfolded conformer. And we have a fingerprint of the folding, actually. If we move now to transient near-edge X-ray absorption spectroscopy, and we run this kind of experiment on the K-edge, so we are resonant to excitation of the nitrogens of our system. So we are probing the nitrogen K-edge. This is the spectrum that we obtain. again, we can visualize the signature of the energy transfer, but let's see if we can address some of these signal as produced by the charge transfer state. We have the signal of the unfolded conformer, we can clearly see in the total spectra. We have the signal of the folded conformer. This time they are identical. The only thing that is changed is actually the timing, the lifetime of the state. Then we have the signal of the charge transfer, which unfortunately is again in a crowded region. And then we have this long-living signal of nicotinamide, which can be used to visualize the energy transfer path. If we finally move to the transient X-ray photoelectron spectroscopy, always on the nitrogen K edge, we have now a less congested map. In fact, see that all these kind of signals are spread on a very large energy window. And if we analyze one by one the signal, we have the one coming from the unfolded conformer, which is the dominant one. Then we have the one coming from the folded, from the LA excited state of the folded, which is suddenly depopulated again, but it is basically the same as the one from LA of the unfolded one. And then we have the signal of the charge transfer. This time, the signal of the charge transfer is really structured due to the different distribution of the positive and negative charge that are present in this kind of states. And also in this red-shifted background-free region, we can visualize in the total spectra a clear signature of the charge transfer state. And finally, looking at this pale yellow signal just on the top of the spectra, we can have also an insight on the population of nicotinamide. If we now look closely then to this kind of spectra and we improve the time resolution, so we watch just at these two cuts of the spectra, we can see that we have two different regions of the total transient X-ray spectra that we can use to study this kind of non-adiabatic process. For example, in the first one, we can clearly see a signature of the charge transfer state and also a signature of the energy transfer state, while in the cut number 2, where we are looking just at the background-free red-shifted region, we have just a way to visualize the population dynamics in the charge transfer state. But why we observe such a clear signature of the charge transfer state? Here I reported the electronic structure of this kind of state, which is basically that one, and this implies that adenine is negatively charged and nicotinamide is positively charged. And then if we now try to ionize a nitrogen from the negatively charged moiety of the system, it costs less energy than remove an electron from the positively charged moiety of the system, but also it costs less energy than remove an electron from a neutral moiety of the system. And in that way, we can explain why we are able to visualize a red-shifted signal, because we can say that it is due to the two nitrogens that are in the 6-member ring of adenine, and so where the negative charge is actually placed on the city state. And so if we ionize these two nitrogens, we have this kind of extremely red-shifted signal. But in principle, since also transient photoelectron spectroscopy probes this kind of cationic state, it should give us the same results. But if we look at the photoelectron process, and we think to start from these two kind of states, which are respectively the city state and the pi star state of nicotinamide, for example, and we imagine to remove one electron from the LUMO of adenine, as in the charge transfer state, we can reach this kind of cationic state, but this kind of state is reachable also if we remove an electron from the pi star state of nicotinamide. And so we have that different valence excited states can end in the same cationic state. And so in the region of the crossing, they can overlap one with each other, and so the charge transfer state might be not visible. Okay, but for transient X-ray spectroscopy, this is simply impossible, because if we now try to remove one electron starting from the same excited state, but now we are removing electron from the 1s orbital, which is a spectator orbital, we can't simply reach the same core cationic state. And so, due to this fact, we have that the ionization of the negatively charged moiety of the system lead to a redshifted signal, which is only accessible from the charge transfer state. So finally, what we do is to simulate a different time of ultrafast spectroscopy experiment, especially in this kind of energy window. And basically, we use it to try to resolve this kind of energy transfer process. And just to summarize, we see that we can have the fingerprint of the folding conformer in the transient photoelectron spectroscopy. We can have signature of the charge transfer state in the transient X-ray photoelectron spectroscopy. And the reason why we have this kind of signature are general and can be transferred to other systems. So we can use this kind of experiment to probe similar systems. And finally, I would like to thank all the people that are involved in this project, and I would like to thank you for your kind attention.
Questions? Again?
Okay.
My question is concerning response functions.
Okay.
I understood the uses why response functions they transform and the signal. So for optical spectroscopy, I understand it. So there's commutators from different dipoles at different times. What do you use to compute response functions for XPS?
Basically, we use the same approach because in the end, you are right. You have not actually you still have a dipole operator, which is now have basically an element which is a Dyson intensity actually, but still is a Dyson operator. So you can still use a third order response function in order to model it.
Yeah. We also use this, so it's fine. I'm just curious. So it's not really the photo-electron signal itself, so it's just the response function.
Yes.
Okay. Yeah. Thank you.
Okay. No, you're welcome.
All right, I don't see more questions, so join me in thanking the speaker.